lecture.
Okay, thanks. So in this lecture, I should try and state and give some indication of a proof of a modularity lifting theorem. So I should say that yesterday I just made up all the notation in my talk as I went along, and then I tried to check what it was about 20 minutes ago, but I think the link on the website for the scan of the notes is not live, so I just made up completely new notation again. So apologies to anyone who can remember what yesterday's notation was. It's probably going to be close to this, but probably different enough to be confusing, I'm afraid. So let's take P a prime at least 5 for this talk, and let's have K at least 2. And I want to do some kind of modularity lifting theorem for kind of weight K modular forms for p-adic representations. So let's fix rho bar, a representation GQ as I have been doing. So GL2 F some finite field of characteristic P. And let's assume that this is absolutely irreducible, continuous, odd, and I'll put modular in brackets. I definitely need this as an assumption, but this is known because Sayre's conjecture implies this. And this is the same. Sayre's conjecture says that irreducible continuous odd representations are modular. So if we allow Sayre's conjecture as an input, we can remove that hypothesis, but otherwise you should assume for the method that I'm going to make use of that. Okay, let's also assume, for simplicity, that rho bar is unramified outside P. So I'll discuss at the end how to remove that assumption. It's not particularly serious for the method. So now I'm trying to prove some modularity lifting theorem, so I want some representation that lifts this. So let's fix some rho, GQ to GL2 of O. So again, we've got kind of O is OE and F is O mod some uniformizer, where E is some finite extension of QP. So this thing is a lift of rho bar, and let's assume that it is, well, I don't have to worry about irreducibility because I've already assumed that rho bar is irreducible. So this is continuous, it's also already odd, and let's assume it has the same property of being unramified outside P. And again, I'll say something at the end about how to relax that. And to prove it's modular, we need to impose this extra condition of being de Rham at P. And in fact, I'm going to impose something slightly more, which I think I mentioned briefly yesterday. So let's assume that when I restrict to a decomposition group at P, then this representation is crystalline, and it has Hodge-Tate weights. 0 and K minus 1. So what this means is that it kind of looks like rho should come from a modular form. Well, the idea is that these conditions actually specify the weight and the level of this. So the condition of being unramified outside P will mean that the level of this modular form should only be divisible by P. And in this condition, this is crystalline, which I haven't really talked about at all, but morally what crystalline means in the modular form world is level prime to P. So it's got level prime to P, and it's also got level which is only divisible by P, so it should have level 1. And then the weight is given by the Hodge-Tate weights, and the weight will be K. So I want to prove that there's some modular form of weight K and level 1 whose p-adic Gauss representation is this representation I'm given. Okay, so here's where I'm going to probably deviate from my notation yesterday. So I always wanted to assume when I did some Galois deformations, I wanted to only allow ramification at a small set of primes, and here the only ramification I'm going to care about is at P. I mean, the representation I'm looking at is unramified outside P. So yesterday I had a kind of this GQS, where S was some finite set of places. So here I'm just going to let S be P and infinity. I don't remember whether I talked about infinity yesterday, but this is the absolute Gower group of the maximum extension unramified outside P and infinity. So I can write rho bar as a representation of this. And then thinking of it as a representation of this group, there's a universal deformation of this. So this GQP infinity to GL2, something I'm going to call R universal. And if I restrict it to GQP, let's make a further assumption here actually. Let's assume that this is also absolutely irreducible. Again, for simplicity, it's not so hard to relax this assumption. I probably won't talk much about that. So if this is absolutely irreducible, then I get a representation which I don't seem to have given a name to, but let's call it rho P from GQP to GL2 RP. So this is the universal deformation. It's a local thing. And then I'm going to have something that I'm going to call RPK. So I'm not sure how much of this notation I'll then go back and use, but I'll introduce something. So a representation to RP of K. And now this is going to be the universal deformation, which is crystalline, for things which are crystalline with Hodge-Tate weights 0 and K minus 1. So let me just redraw my favorite picture from yesterday. So this whole thing here will be spec RP, and then this RPK inside there is just going to be some finite union of one-dimensional components. I guess again I'm fixing determinants, but I'm not even going to bother writing that, I think. The level of detail I'm talking at, that's not really going to matter. Okay, and then I have the kind of global version of this, which is this, something I'll call maybe RK universal, which is just given by the tensor product of R universal over RP with RP of K, and that has a universal deformation as well, which maybe I won't even give a name to for now. So that goes to GL2 RK universal, and that's the universal deformation to representations which are unramified outside P and are crystalline with Hodge-Tate weights 0 K minus 1 at P. Okay, so going back, we have a representation, a fixed representation we want to prove is modular. And so that gave us a representation by assumption. It was unramified outside P, so we can think of it as a representation like this. And it satisfies these conditions. This is an example of this. And that means that by definition, or by the universal property, this representation just arises as a point of this ring. So it arises from some homomorphism. It's the homomorphism RK universal to O. Maybe I'll call that theta again, such that rho is isomorphic to the composite of theta, and maybe I now should give this a name. I'm not going to use it again, I suspect, so just R. Okay, so the way that we've defined this deformation problem is exactly captures all of the representations which are unramified outside P and have this condition at P. And since the representation we started with is of that form, it arises in this way. Okay, so we want to prove that this comes from some modular form, and the modular forms we care about is going to be the space of modular forms of level prime to P, weight K, and as in maybe as in Frank's talks, there's a nice theory of p-adic modular forms. In this case, I just want classical modular forms with p-adic coefficients. So instead of having forms with complex coefficients, I'm just going to think of them as having p-adic coefficients instead. And then I'm going to do something else, which is I'm going to take the rho bar part of this. So what does this mean? Let me briefly kind of explain what this means. So the idea is that I'm just going to stick to kind of modular forms whose Galois representations are congruent to rho bar. But how do I actually do that? Well, if I let T be the kind of Hecker algebra given by a polynomial ring just with some formal variables, maybe call them TL and SL, L not equal to P, then T acts on this, SL2Z, acts on this space of modular forms just via the usual Hecker operators. So TL is the L001 Hecker operator. This is the kind of L00L1, and maybe let's write M for the maximal ideal T generated by I'm going to put P into it, and then I'm going to put the kind of TL minus the trace of rho bar of frob L and SL minus, so if I can get this right, the norm of L, sorry, no, just L times the determinant of rho bar of frob L, like this. So I'm abusing notation slightly because this is something mod P, but since I'm putting P into this ideal, that's not going to be a problem. So this is a maximal ideal, and then I'm just going to set this space to be what I get when I localize it at M. Okay, and let's maybe let TK be the image of T in the endomorphisms of this. So rather than being some huge polynomial ring right now, this is just some nice finite O algebra. And let's let TKM be kind of TK localized to M. Okay, so then the kind of the fact, or it's kind of an extended exercise in the notes, is that there exists a deformation, maybe I call it rho modular, of definition of rho bar, as always, which has target in this ring. Well, and it also has some particular property. So, for example, the trace of L is just the same as the TL, and the determinant, I guess, is L times SL in here. So, if instead of having this Hecker algebra over here, I was just taking an individual eigenform and saying there was a Gauss representation like this, then that's just the statement that we had much earlier of the existence of Gauss representations for modular forms. And just this statement here is just the idea that the representations for individual eigenforms kind of just glue together to give a representation like this. Okay, well, this deformation is unramified outside P, and it's the usual thing of crystalline with Hodge state weight 0k-1 at P. That's just because it's made from putting together the Gauss representations for modular forms of weight k on level 1. And that means that, that we naturally have a map from whatever I was calling my, I think it's RK universal, mapping to this TK, that gives that Gauss representation. And in fact, because this thing here is generated by the TLs and the SLs, and you can see that they're coming from this Gauss representation, it's actually easy to check that this is a surjective map. Okay, so our original representation, or original deformation, rho, corresponded to a point of RK universal, so a point of spec RK universal. So we have RK universal to O. This is the thing corresponding to rho, which I maybe called theta earlier. I've got this surjection over here. And what I would like to know is whether this factors through here. So rho is going to be modular if and only if question mark exists. So if and only if this homomorphism here can be factored through this thing. And that's because the representations that factor through here are just the representations that come from the modular forms. Okay, so going away from just having any old, we have some rho, we could just take any other rows with this property. So what we need to prove, what we would like to prove, well, if this should be true for all, this should basically be true for all the kind of homomorphisms that I could take to O. There's nothing special from a commutative algebra point of view about the one I've just chosen. I mean, I haven't told you anything about it. So really what you want is something very close to this map here being an isomorphism. So we would like to prove maybe this is actually an isomorphism. Because then it would, of course, be automatic that this homomorphism factored through here because there would be nothing to say. So in fact, this is a bit much to hope for, perhaps, and a bit much to try and prove. So we only need something weaker. And that's that I'm not going to worry about the possibility of any nilpotence. So if I have the reduced quotient instead, I could ask whether that's an isomorphism. So I should say this Hecker algebra here was just by definition, it's just the localization of some finite O algebra living inside this endomorphism ring. And so it's certainly reduced by definition. So this homomorphism factors through the reduced quotient. And this question about O points never sees anything to do with nilpotent elements. So it's enough to prove this. So this is kind of the target of what we want to prove. And this is This is what's called an R equals T theorem. So in Weyl's original work, he actually really proved an isomorphism like this, that really was an R being equal to a T. But these days, kind of, in some sense, the techniques have got better, but as that's happened, the range of situations we've extended to has become more complicated, and you no longer expect to be able to actually get this on the nose anymore. Instead, you have things like this, but it's kind of more cumbersome to sort of say an R reduced equals T theorem or something. So we still talk about R equals T theorems. Okay, so what I want to do is sketch how we prove this. So maybe I should kind of give you an example of the kind of things that could be coming up. Well, I think the prototypical example you're supposed to keep in mind is that there could be a situation where maybe this, when I say in general these guys are going to be equal, but so if I give you an example, I should sort of say it's applicable to either of them, but you could think of as being kind of is typically something like the following. So it's something like maybe the ring given by pairs R and S in ZP squared with R congruent to S mod P. So that's kind of the classic example you're supposed to think about. So, I mean, you might want to, as a very first approximation, you might want to think about a very simple situation. If we had a very simple situation where there was really just one modular form of level 1 giving rise to our mod P Gauss representation, then the deformation ring would just be ZP, and it would just have, or yeah, if I forget about the coefficients, it would just be ZP, and there's just one homomorphism, and everything's very simple. So this kind of situation is the situation you would get, is if you just have kind of, there are two modular forms, kind of F and G in SK SL2Z with, when I say two modular forms, I mean two eigenforms with Gauss representations congruent to rho bar, so that F is congruent to G mod P, as it were, but F is not congruent to G mod P squared. So if you imagine that kind of situation, which really does happen, I'm sure there are people here who tell me that if I took sort of modular forms of weight 2 and level 37 or some random guess like this, that there would be examples like this. I don't know these examples, but these things really happen. And then this condition down here just translates into this thing up here. So that's the kind of rings we might be dealing with. Of course, in general, you could have lots of eigenforms with lots of congruences between them, possibly modulo different powers of P. And then the problem is to kind of get any control, get some control on R, on RK. So we want to prove this thing's an isomorphism. Basically, what you can imagine is that there are kind of two directions you could go in. You want to kind of prove that every Gauss representation is modular. You know that all the modular forms give you Gauss representations. You either have to kind of prove that there are lots of modular forms or that there aren't too many Gauss representations. You have to squeeze the two things together. Okay, so essentially it's kind of very hard in general to actually compute this explicitly. And what's easier, at least in many cases, is to compute the local deformation ring instead. So it's to compute what I called RP of K this morning. So this is the local thing with the crystalline condition. So these are just these finite union of components inside my cube. So then somehow the strategy is to kind of study the image of spec of the global global deformation in the local one. So there's always this map from the global deformations to the local ones just by restricting to the decomposition group. You can understand what's going on locally, and then you can try and understand what's going on globally by viewing it inside the local thing. So, okay, so it turns out that in considerable generality, I have to confess I don't know quite how generally this statement is true. The map from the global space to the local one is a finite map. So for the moment, just for exposition, let me assume something stronger. This is kind of a temporary assumption, that it's actually not just finite, but in fact a closed embedding. So the global deformation is actually just a quotient to the local one. So that's not so unreasonable, closed immersion. Then you could actually check this. So when does this hold? This condition can be checked on tangent spaces. And thankfully, tangent spaces are about the only thing that's easy to compute, easy to get your hands on about these rings. So you can really get your hands on the tangent space of this. So why is that? Well, to compute a tangent space or a reduced tangent space, what I need to compute is the following. Basically, the OHOMs from this ring maybe to the dual numbers over FP. This is the kind of thing I want to compute in order to understand the tangent space. But this has a meaning. So this is just what you would do in general for a general ring, but homomorphisms from this universal deformation ring to a particular ring are just the same as deformations to that ring. So we need to compute deformations of rho bar to this ring. So that's the kind of thing we'd like to do. And that is the kind of thing you can really get your hands on, because you just write such a representation as rho bar plus epsilon times something, and you write out what that something has to satisfy, and it means it's actually like a cocycle. So you can compute this in terms of Galois cohomology. And so in fact, to get this map to be a closed immersion, so the condition for it to be, for this map to be an immersion is the following. So the following Selma group is trivial. So if I take the kernel of the H1 of GQ P infinity on add 0 rho bar, which I'll explain what that is in a second, to the local cohomology group, I want that to be 0. So this is some Selma group. I'm looking at all the cohomology classes unramified outside P, which in fact become trivial when I restrict to P, and add 0 is just the trace 0 HOMs or elements of the HOMs from rho bar to rho bar. So as a four-dimensional Galois module, I take just the trace 0 part. The reason I've got trace 0 is that I've implicitly fixed determinants everywhere without ever writing it down. It's not a particularly significant thing. I could just have add rho bar there instead. Okay, so this is some condition. I don't know quite how generally this condition holds, but I think it's pretty reasonable to suppose that if you, for example, just like fix a modular form and look at all of its mod p representations as p varies, then probably for maybe all but finitely many, or but for at least the density one set of primes, then this condition will actually hold. So it's probably a reasonable assumption. And it's not one we're going to have in the final theorem. But if we make that assumption, then I've got this embedding, and now I can kind of draw the picture I had before. And I can study everything. I can draw a cube at least. I can study everything inside here. So here's my universal space. Here are my local things. Here's my universal local space. Here are my crystalline components. And now I'm going to draw the global thing inside here. So this is where we're going to really run into the shortcomings of my artistry. But this thing here is some two-dimensional thing, and this is actually, so in fact, if I have this embedding, this closed embedding here, I in fact get the same thing if I remove the k's under the conditions I've written down. So this thing here is just the, whatever I call the universal thing. So the universal thing is some two-dimensional sheet inside this three-dimensional space, and then the intersection, so let me try and just draw some dots. So this kind of finite set of points here, so the points is where this this universal crystalline thing is living. So this two-dimensional sheet here is all of the global representations, which are unramified outside P, but I haven't put any condition at P in. Similarly, this thing down here, these components here, are the ones which have this crystalline condition. And then by definition, the intersection of those things is the global deformations which satisfy this crystalline condition. Okay. So this is all well enough, but the kind of the issue that you run into now, well, if you want to use this picture in some way, perhaps the problem is that the points we really care about, the things we really care about, is just some discrete set of points. So we have this nice two-dimensional space here, we have these nice one-dimensional spaces here, and these one-dimensional spaces are things that we can really actually hope to understand. But then the intersection is just some finite set of points, which doesn't really have so much that you can, it's hard to really make some amazing argument just using a finite set of points. So then the idea of the Taylor-Wiles method is to allow the level away from P to vary. Okay, so what I now do is I now relax the condition that my deformations were unramified outside P. So I choose a prime Q not equal to P and kind of repeat the above constructions. Now allowing my deformations to ramify away from, to ramify at Q. Well, it turns out, and this needs a little bit of an argument, but it turns out that you can choose Q. I mean, if you do this in a completely arbitrary fashion, one problem you'll run into is that this Selma group that I had back here, there's an analogous Selma group where I now put a Q over here as well. I allow ramification at Q, and I still want that thing to vanish in order to view all my global things as being inside my local space. But it turns out that you can certainly choose infinitely many Q for which is still an embedding. So you can choose Q, so the map is still an embedding. And then you get a picture like this. Maybe I'll just draw the global sheets and not worry so much about the local ones for a second. So maybe here's my first thing. But now, every time I choose a different Q, I get a different global sheet inside here. Maybe I should just draw 2 sheets, because if I try and draw many more, it's going to become a complete mess. But what you should imagine is that there are kind of infinitely many primes Q I can choose, and each of them gives me some 2-dimensional slice coming through, okay? And so then the idea is, if I look at my local components, I now, for each prime Q, I now have some finite set of points. And as I'm doing this with lots and lots of primes Q, I'm really going to manage to fill out each of these things with a dense set of points. So letting Q vary, we kind of fill out. So I guess we fill out the whole deformation space, spec RP, with the images of the global deformations. Okay, so now we've got all these primes Q, and we've got all these slices across, and we've got all these points on these components. And now you do something rather remarkable. You now patch these spaces together, or patch everything, I should say, everything together as Q varies. And in particular, we patch together the spaces of modular forms. And now, well, what modular forms am I considering? I'm allowing ramification at Q, so basically what I'm thinking of doing is sort of allowing maybe level gamma 1 of Q instead of just level SL2Z. So I'm going to be completely vague about what I mean by this. It's a slightly weird business, because we're varying, as we choose different primes Q here. I mean, all of these spaces of modular forms you can compare to the space of modular forms at level SL2Z. They certainly contain those, but you can't compare them to each other. If I sort of think about modular forms where I allow some level structure at 3, or some at 5, or some at 11 or something, there's no natural maps between any of those things. Okay? So it's rather hard to imagine how I'm going to glue them together, and the answer is we're going to do something completely ridiculous. Is because we put everything inside this local situation, I can just think of all of these spaces of modular forms as being modules for this local deformation ring, RP. Okay, so these are all modules. These all have some action of RP. And now I can just kind of forget that I'm doing anything to do with modular forms or Gauss representations at all, and just say, now I have some infinite collection of modules over this local ring, and now I'm going to try and glue them together in some completely formal way. So basically the idea is that I'm not going to glue them together quite as they are, but maybe I'm going to glue them together mod P, for example. And once you take everything mod P, everything just becomes a finite situation. You put yourself in a situation where you have a finite ring and modules over it of bounded rank, and then there are sort of only finitely many isomorphism classes. So it must be possible to just glue a load of these, to identify a load of these things in a non-canonical way. So I start identifying all these spaces together just as modules over this ring. This is purely some abstract thing, nothing to do with Gauss representations of modular forms or anything. But the kind of output that you get when you do this is maybe something I'll call M infinity, maybe with a K on it, which is a module over RP, or perhaps I'd rather think of it as a sheaf. Sorry, RP. How was I decorating that with a K? Was I putting it in brackets? Yeah. So RPK, a sheaf over the spec RPK, and it's built out of the spaces of modular forms. These spaces here. Okay, and then what kind of comes out from the commutative algebra is that this sheaf, the support of this sheaf, is, well, you can kind of guess what it's going to be. The idea was that to start, I had these one-dimensional spaces over which this thing lies. And to start with, I had discrete sets of points, but then I was kind of getting more and more points as I did more and more global situations. So you should imagine it's going to fill out the whole thing in some sense. So I can't quite say that it fills out the whole thing, but I can say that it's a union of components. Of this local thing. So in some sense, it would be too much to hope that I'd managed to prove that it was supported on all the components of this, because I've not really done anything. I've not really said anything about the structure of this thing, and that would be saying that I had modular forms with lots of, I'd be able to specify something about the local Gauss representations of modular forms in some very delicate way. But what I can say is that basically each component is either covered by this patch space of modular forms, or it doesn't see it at all. Okay. So one day I'll draw a cube that looks actually like a cube, but probably not today. So here's my local things, and now let's imagine that the sheaf is just supported over some of these components. Okay, but this poor component here hasn't been covered at all. So I should say that while this is the kind of picture that could theoretically arise, in practice when you do this, we all believe that you really will cover all of the components. Somehow if this didn't happen, it would contradict a lot of widely believed conjectures in number theory. But now, so now kind of return to finite level. So somehow I think of this as being some process where I've kind of gone to infinite level by adding all these different primes in some way. If we go back down to the original situation and intersect like this, you can kind of formally deduce, again, just from the commutative algebra situation, that that each point of the global ring we cared about that meets, that lies on one of these components here. So one of what I'll call maybe the supported components is modular. So the idea is, I built this by gluing together all these modular forms. So the idea is that if my point is over here, then it really is given by a modular form. But I'd be in trouble if I looked at this global Gauss representation here. This global Gauss representation would in fact be an example of a representation that contradicted the Fontaine-Mazur conjecture. So it'd be some representation that had the crystalline condition but wasn't modular. Okay, so to kind of prove the theorem, to really prove the kind of theorem you want to have, now what you have to do is you have to prove that this support covers all the components. So now we want to prove that M infinity K is supported on every component. And what we do, at least for the purpose of this talk and for the notes for this course, is now we cheat, in some sense, because what we do is we say now that we're going to fix K to be at most P minus 1. So let's assume this. Then you can use what's called Fontaine-Lafay theory. And that implies you can use Fontaine-Lafay theory to actually compute completely explicitly this deformation ring, this RP of K, and you can compute, and it just has one component. But if you have only one component, there's no problem. Okay, the support is on that component. There's nowhere else for anything to run away to. So that implies the kind of modularity of rho in this case. So in the last few minutes, I'll just briefly say how to relax various of these conditions to make an actual useful theorem. So one thing I did is I assumed that this Selma group vanished. Okay, so how do we relax the kind of remaining conditions, the kind of extra conditions? So the extra conditions I have in mind are basically that condition about the Selma group, and also I assumed at the beginning I was unramified outside P, which is a bit too strong an assumption to really make in general. So if the Selma group doesn't vanish, well, what you basically do is you kind of artificially make your deformation space bigger, your local deformation space bigger, just by adding in extra smooth directions. So what we do is we replace this local deformation space with, or spec R of P maybe even, with spec RP, adjoin some, let's just add some power series variables. So basically, I mean, we had this finite map from the global thing to the local thing. If I just give enough smooth directions, I can smooth that out into being an actual embedding. And then what you do is instead of using I was putting in one prime at a time in to get these extra sheets, you end up then having to put in more primes to kind of fill out the extra directions you put in. So we use kind of multiple primes, Q1 up to QS. And if we allow ramification away from P, then what we do is we also bring in the local deformation rings at those primes as well. So then we kind of also consider the local deformation spaces at the ramified primes, at these primes where we're allowing ramification. And then basically you do the same construction, except now you have your, wow, my cubes are really just going to get worse if I carry on much longer. Basically, you're then going to end up with, and these shouldn't really, maybe these spaces are going to be a different dimension. Let's draw squares, maybe, I don't know. Jeez, right. Okay, so you have some spaces at these primes where I'm allowing ramification as well. And you'll do the same construction, and what you'll end up with is knowing that your sheaf is supported over kind of a product of components. So there'll be some components over here, and some components over here, and components over here, and you have a product over all of them. And now you need some extra arguments, but basically now the question is one that's to do with level raising and level lowering that will come up a bit in the project talk tomorrow. So there is a solution to this problem, but there's a non-trivial issue, but it's known how to get around it. So maybe the final remark I'll make is just to say that, I mean, this is all just presented with modular forms of a GL2, but exactly this same picture exists for now for n-dimensional representations. You can work with unitary groups over arbitrary CM fields and so on. And this is really the kind of formal picture you get. And this is exactly, this Taylor-Wells argument gives you exactly this thing. But then the problem in general is that, I mean, this is the reason I restricted to a small value of k. So in general, I get a picture like this. I get a bunch of components, and I need to understand when this sheaf is supported on each of them. In general, the problem is that you cannot compute these spaces in any kind of explicit way. So we don't even know how many components there might be. We don't have any real control over them. But you can still do things, but that's kind of maybe the biggest problem in making these theorems as quite as explicit as you would like in general, is that we don't really understand these deformation spaces at P. So in this case, I did this 1 times the phi thing of just saying there was just one component. But in general, I think that's a really big open problem. Okay, I'm a couple of minutes over, so I'll stop.